Okay, so last time we discussed about this convex concave saddle point problem. This is a very interesting class of optimization problems where we have a bivariate function fxy. Okay. And we want to maximize over y but minimize over x. So this is the model that people use to model games, general games, where two agents are competing with each other. One wants to maximize the profit, the other wants to minimize the cost. The profit of one side could be the cost of the other side, and they are competing through this minimax game. And in this case, there are many formulations of this type of problems. Here we consider the convex concave case, where the f is convex in x and the concave in y. And for this, this is an example of a saddle point problem. And the optimal point x star, y star satisfies this criteria. Okay. So x star, you can say that x star is the best response to y star, and y star is also the best response to x star. And we introduced this projective subgradient method for this saddle point problem. The algorithm is pretty straightforward. Since we are doing minimization over x, so we simply perform subgradient descent on x. So this on the first row we are doing subgradient descent. So this is a minus sign. On the second row, we are doing subgradient ascent because we are maximizing over y. And the convergence metric we discussed last time is given by this duality gap. It basically measures how far a point is, like a given xy is from the optimal saddle point. Okay, and we call this the duality gap. So our convergence result is about this duality gap. So here we are looking at applying the projective subgradient method to solve a convex concave Lipschitz saddle point problem. And assume the variables x, y are in a bounded sets. Then for this method, the duality gap in the tth iteration is bounded by the following. So first of all, we are looking at the duality gap at these 2 points, x hat t, y and y hat t. Well, x hat t and y hat t are weighted average over the xt's generated in the previous t iteration. Okay, so you run this projective subgradient descent, right? You will have a sequence of x and y's in the t iterations, and then you average them using this weighted average. You average them over with the coefficients given by the step size. Okay, and their average will give us this x hat t and y hat t. And the result says that the duality gap at these two weighted average points is bounded by the right-hand side. The right-hand side is very similar to what we have for projected subgradient method for convex problems. So the rate depends on sum of the squared step size to the power of 2. This is squared step size over sum of the step size. We have seen similar bounds before. So this means if we pick a proper step size, for example, if we choose eta t to be 1 over square root of t, then this is roughly log t over square root of t. Okay, so the convergence rate is the same or very similar to that of convex optimization problems for subgradient descent. Okay. And here, the special thing is that we are looking at these weighted average points, right? This means if you run this algorithm for t iterations, you will have x1, x2, x3, right, up to xt. And then we look at the weighted average of these points, not the last iteration. And turns out that this is very crucial. This is a crucial design. So it is crucial to output the weighted average instead of the last iterate, because if we look at the original iterates, this xt yt, this sequence may not converge in general. We can have some simple examples. For example, the following bilinear game. And we can show that if you apply this subgradient descent method to these algorithms, the xt yt will not converge. And it will have a cycling behavior around the saddle point. It will keep wandering around the optimal point and never converge. But if you do this weighted averaging, these averaged iterates, they will converge to the optimal point. So this is a special key difference for these convex concave problems. So now let's briefly look at this convergence analysis. Because for this problem, we have two sides, right? A minimization side and a maximization side. So there are two players, and they are kind of symmetric. So the analysis is also kind of symmetric. We will first build these two inequalities, symmetric inequalities, by utilizing the convexity and the concavity of the function. So the first function, we fix yt. Now this is inequality following from the convexity of f in x, right? Because for every fixed yt, function f is convex. So the first inequality is simply convexity. I plug in xt and x, and this is by convexity. Now the second inequality, we fix xt, and then the function is concave in y. So this is essentially concavity, based on concavity of the function in y. And you see these two have different signs. This is xt minus x, but this is y minus yt, right? Because this is concavity. Okay. And then we add them together. So this term will cancel out. This term will cancel with this term. So left-hand side, we only have a difference of function values. And then these two inner products. Okay. And then with this inequality, we can start to bound the duality gap. So let's look at this one. By definition, the duality gap at x hat, y hat t is defined in this way. Okay, this is simply by definition. Okay, and now let's write it down here. So we have max over y f. Now x hat t y, I can plug in the definition of x hat t. Go back to the theorem. This is x hat t. So let me write it. Let me copy it here. Okay, I will skip those summations, the summation over tau for simplicity. So this is x hat t, right? Y minus mean over x. And we do the same thing. We have x. And for y hat t, okay, again, by definition, y hat t is a weighted average over y tau. But I think I will just do one side. The other side is the same. Now, for a fixed y, this function is convex in x. Therefore, and look at this weighted average. This is a convex combination of all these points x tau. Right, this is basically sum over eta tau divided by sum over eta tau x tau. This, you can check, this is a convex combination because these coefficients, they are non-negative, they sum up to 1. Right? When you sum over tau, they sum up to 1. Because the denominator has that summation as a normalization factor. So this is a convex combination of all these x taus. So by convexity and f, but f is a convex function in the first variable. So by convexity, by the basic definition of convexity, we can simply, the function value at a convex combination is less than or equal to the convex combination of all of the function value at these individual points. So what I'm going to do is this. The tau f x tau y divided by sum of eta tau. This is simply by convexity. And that's why we get the second line, this part. You can check they are the same. Sum over eta tau f x tau y. That's the denominator. Numerator is the sum of eta tau. The other part, you do the same thing, but now you are using concavity of f in y. The y hat is again a convex combination of all the points. So it's the same thing. Concavity is negative convexity, so there's no difference. Okay. By doing so, we end up with what? Now this is a common factor. We can pull it out, and inside we have these two difference. Okay. And then this is exactly what we have here. Right. Now this inequality holds for any y and x, right? For any y and x. So here we are, although we are maximizing over y and minimizing over x, but you can assume a certain y and x achieves this maximum and minimum, okay? And then you utilize this inequality because it holds for any x and y. Once you utilize that, these two summation, okay, becomes what? Sum over eta tau, and then you have x, this f minus subtracts that f. That becomes this inequality, which can be controlled by this the difference of these two dot products, right? So you end up with this structure in the last inequality. Okay, so this comes from this inequality. Okay. Right. So you end up with this one. Therefore, we just need to bound. So this is, again, right? The starting point is the duality gap. So we just need to bound 4.7. We just need to bound 4.7. And this lemma provides such a bound, where this lemma controls 4.7, like this term. Okay. So with this lemma, you plug this bound into the last line, you get the desired result. Okay, you get the desired result. So everything reduces to proving this lemma. And the proof of this lemma is also takes several steps. Okay. But let's look at this one. We want to control this type of structure. It's a difference of these two inner products, which is a little bit, looks very complicated, but see, here's a very nice observation. This structure, right? This is exactly what we have in that lemma. Let's go back. Right, gx tau x tau minus x. We have exactly these terms here, right? This structure can be related to this addition or subtraction of these quadratic terms, because what happens, you can view this as the cross terms comes from several quadratic terms. When you expand square terms, right, you always have cross term, and it turns out that these two can be related to these quadratic terms. And to be more specific, now this is a big idea. Okay, how do we prove this one? Specifically, we start from this quadratic term. Okay, x tau plus 1. This is in the tau plus 1 iteration. Now, plug in the algorithm update. X tau plus 1 is generated by one step of projected subgradient descent. Okay? And x is in the set x, so I can add a projection for free. And then I know projection on preserves the distance, so this is non-expensive. So I can just ignore the projection and then subtract these two, the variables inside projection. And then for this quadratic term, I can expand it, okay? And I get these three terms. Then rearrange this inequality. Now put this inner product term on the left-hand side, put all the other terms on the right-hand side, I end up with this one, right? This shows that we can bound this type of inner product using a bunch of quadratic distance terms. And similarly for y, for the y update, you have a very symmetric structure, so you can end up with this very similar inequality. Okay. And then you add them up. This will give you this final result. And all these subgradient terms, this subgradient and that subgradient, they are bounded by a constant LF, the Lipschitz constant of the function. Okay. So this is how we control these inner product structures. Okay, now continue. We simply we need to sum these inner products over tau, right? So let's do a summation. So sum over tau. Now on the right hand side, you will sum these terms over tau, right? Many terms will cancel. Why? Because you have this difference terms x tau minus x tau plus 1. So the intermediate terms will cancel. Only the initial and the last terms will remain, right? So once you do a summation, you only have the first term and the last term. And then this is another summation over the last term. Okay. And you can drop these two terms because they are positive. Okay. So this is less than equal to these two initial terms plus the last term. And this is bounded by the diameter of your domain because both of them are in X, X0 and X. Both of them are in X. So you can control them by the diameters, and that is what we need. That proves this lemma. Okay. And combining this lemma with that with this inequality, we can get the desired result. Okay, this is the final result. So you see, it's not the proofs actually follows a very similar structure. Basically, convexity and utilizing the subgradient, the descent update rule. But now we have both x and y. So for the y part, it is essentially symmetric to the x part. So there's no key difference in the proof. Okay. So this is the saddle point problem. And yeah, I think that's everything for the subgradient method that I want to talk about. So we can see that even for the saddle point problem, subgradient methods can still achieve a 1 over square root of t convergence rate. If you use this step size, this convergence rate is pretty much the same as the previous one. Okay, and with this, you can work on homework 3. No, actually homework 4. Yeah, I'll just briefly talk about this. There are two simulations. One simulation comes from the lecture notes where we are looking at computing the eigenvalues, leading eigenvector of a matrix. Okay, you just follow the instructions to generate a positive semi-definite matrix and follow the algorithm to implement the algorithm. So I think simulation 1 is pretty straightforward. Now simulation 2 is to apply the projected gradient descent to solve a constraint least mean square problem. And here you can reuse the code that you generated for homework 2 and modify it, because the problem we are looking at is a generalization of the previous homework. So you can modify the code based on that. So the only difference is that we are solving this problem, the same problem, but with such a constraint where we require at the infinity norm of x is less than 1, which means the maximum entry, the entry of x with the maximum magnitude should be less than 1. And here I give you a hint on how to do the projection on this infinity ball. Okay? Because when you implement this projected gradient descent, you need to do a projection. Now, the question is, what is the projection? How do we project a point Z onto a L infinity ball? And this is something that you want to look into. This is a step-by-step derivation of the projection. This is the original definition of the projection. We are looking at, given a Z, we are looking at the point, or the point X that has the minimum distance to Z within that set. And then this problem can be decomposed into this way. So you can check. The L2 norm is basically sum of these squares. L2 norm square is the sum of squares. L infinity constraint is basically, if we write it out, is basically restricting all the coordinates to be less than 1. The magnitude of all the coordinates to be less than 1. And this can be done one by one because all the constraints are separate, are kind of separated with regard to all the coordinates. So you can simply optimize each of them one by one. And following this, you can derive a formula for this projection operator. You simply, now this problem is simply a one-dimensional optimization problem. Right? Zi is given, and you are looking at between -1 to 1, you are looking for a point xi that is closest to Zi. You can derive a formula for this. There's a closed form solution for this small optimization problem. Yeah. And once you identify the xi, once you identify the closest xi to each zi, those xi's, you concatenate them together, that will give you the projection. Right? Because you are projecting Z onto this high-dimensional ball, right? Once you solve this small quadratic one-dimensional projection problems, you collect all those coordinates that will give you the projection, the final point. Okay, so you can program, once you have this analytical formula, you can program it into the MATLAB or Python. So you can write a function that takes any point Z and outputs the projection onto this ball. Right? With that, you can do the projected gradient descent. Okay, so this is about the homework And next, we'll go to lecture 4 and talk about a very interesting generalization of the subgradient methods or the mirror descent. Okay, so let's go back to the method of gradient descent first. So remember the simplest gradient descent. This is the update rule. Xt plus 1 equals xt minus eta t gradient f xt, right? This is very basic gradient descent update. But in fact, this algorithm has a very nice interpretation. Okay. And we usually write this algorithm in this way. Okay. This is exactly the projected gradient descent. Sorry, let me actually add a projection here. Okay, it's more general. So projected gradient descent. This algorithm update can be rewritten in this form. And in this form, we describe the algorithm by an optimization problem. And the idea is that you give me an xt, I construct this optimization problem. And the solution to this problem is my next iterate, xt plus 1. And turns out that the solution of this problem is exactly this update rule. It's exactly taking a gradient descent and then do a projection. To see that, we can start from this part. If you look at these 3 terms, right, we are looking at this is a optimization problem in X. We are looking at the minimizing over X within the constraint. So xt is fixed. It's given by your previous iteration. So xt is a constant. We are doing minimization over X. Therefore, the first term is simply a constant. We don't need to care about it. fxt is constant. The last 2 terms matters. So let's write down the last 2 terms. And you can tell that this is a quadratic optimization problem because the first term is it's linear in X, the linear term. This is a quadratic term. So in the end, it's a quadratic problem. And we can complete this this square. We complete these 2 terms into a big square term. This is like a cross term. So what? So we have this square term, and we need another gradient term, right? So I can do the following. I can do the following. this is equivalent to so because I'm looking at this minimizer of this function, so I can add any constant for free, right? So I can just add gradient f t square, and then this will be I will skip this inner product. This is the dot product term, and this is that quadratic term. Now, then I need to be a little bit careful. I need to make sure this is a complete square. So let's look at this one. The dot okay, this term has 1 over eta t, but the inner product term does not. The coefficient is 1, so I need to make sure I get the correct coefficient, right? I need to introduce 2 eta t to the first term, and then um, okay, and then let me see. I can write this as um, okay. Okay, I got it. Maybe I'm doing it in the wrong way. So what I'm going to do, so okay, so I can do the following. Now I can so starting from this line, I can multiply the problem by 2 eta t, because scaling all the terms by the same constant does not change the problem, does not change the minimizer. I can multiply all these terms by 2 eta t. So that this becomes 1, this term becomes 2 eta t, and then I can introduce another constant term. Doesn't change, it does not, all these operations, right, does not change the minimizer of the problem. Think about that. If you are minimizing x squared, it is equivalent to minimizing 5 times x squared. It doesn't matter if you multiply the problem by a constant. And if minimizing x squared is equivalent to minimizing x squared plus 5, it doesn't matter if you add a constant. So these are constants that I introduce to the problem. That doesn't affect the problem that we are solving. Okay, and then this is a complete square. This is essentially x minus xt plus eta t. You can check, right? You can just expand this one. You have square term. Okay. This means I need to add eta t squared to the first term. You can check that this is the square term of here, and eta t gradient is this term, and then the cross term. All right, so this is a complete square. So this is arc name x belongs to C that. And look at this. This is exactly the projection operator. This is exactly projecting xt minus eta t gradient fxt. Projecting this point onto the set C, right? So you view this as a a given point. This is x minus what? X minus xt minus eta t times gradient. And this is x minus xt minus eta t times the gradient. Right, so it's x minus this term. This is a given point. And we are looking for the x that has minimum distance to this given point within the set C. So this is by definition the projection of this point onto C. Right, which shows this is exactly the projected gradient descent update. Okay, so this shows that this is exactly the another way to rewrite the projected gradient descent method. And why do we want to rewrite it in this way? Because this is essentially this equation illustrates all the designs of this algorithm. Okay. At every point xt, I construct a quadratic, like this is like a Taylor expansion up to the second order. It's a local approximation of your function at xt. So like inside is you can view it as a Taylor expansion or local approximation model up to a quadratic term. And so instead of working on the original problem fx, we construct a local approximation of the problem and solve that simple problem. Okay, that is the key. Actually, all the optimization algorithms follow this key logic. Okay. Instead of working on the original problem, every time you construct a local approximation of the problem, solve this local approximation. You solve this local approximation, and the solution will be your next iteration. And once you go to the next iteration, again, based on that new point, you will construct a local approximation. So this model, this local approximation model, keeps updating over the iterations because xt will change over time. And this xt will change over iterations. So this model keeps changing, and it will be adapted to the local, the model will be adapted to the local geometry of the problem. So this is the philosophy of designing this optimization algorithm. So this red, okay, the blue is your optimization problem. And this red curve illustrates this this quadratic model, right? This red function is this quadratic model you constructed at xt. Okay. And a very natural question to ask is that this part is given by Taylor expansion, and then this is kind of the residual part. It's a higher order term on this on the difference. Now, there's no reason to only use this L2 norm in the last term. But you can use any norm following this strategy. As long as it's something higher order with regard to the previous terms, then it should be okay. So the key question here is that what else can we, what other distance metrics can we use for the third term, for the proximity term? And what is the motivation to use other distance other than this L2 norm? Okay, so in projected gradient descent, as we have shown, right, we use this quadratic term, or more specifically, we use this L2 distance, L2 distance to the power of 2. So it is based on L2 distance, but L2, we have seen in the previous lectures, L2 means that we are imposing a certain prior belief on these variables. Basically, we are assuming that these terms should be measured in a homogeneous way. L2, it means that everything, if you draw L2 ball, think about that. If you draw L2 ball in 2 dimensions, it is a square. It is a round square, means everything is homogeneous, right? But if you draw L1 ball, it corresponds to a diamond. It is not homogeneous, right? So when you use different distant terms, you are imposing some prior belief on this problem. So when you use L2, you believe the problem is homogeneous across the dimensions. But certainly not all the problems fit into this prior belief. There are some problems where it could be highly inhomogeneous. So the issue is that the local geometry of the underlying problem sometimes may be highly inhomogeneous or even non-Euclidean. So for those problems, we still use this homogeneous distance term. It may cause a lot of issues. Okay. For example, we have seen this quadratic minimization problem before, right? So this is well, X star is the minimizer, Q is a positive positive definite matrix. And in the previous lectures, we have shown that if this matrix have a large condition number, right? So denote kappa as the condition number of this matrix, which is the largest eigenvalue over the minimum eigenvalue. In this case, gradient descent has a slow convergence because previously we have shown that maybe we can quickly go to the gradient descent. It should be lecture 1. So yeah. If the condition number is large, meaning that lambda 1 is far bigger than lambda n, the biggest eigenvalue is much bigger than lambda n. So what will happen? Well, the numerator is very close to the denominator. So this number is very close to 1. If this number is very close to 1, then you raise it to the power of t. That will, be that will diminish to 0 very slowly, right? So this is the issue when we have a large condition number. And geometrically, that simply means if you visualize the contour of this quadratic function, it looks like a very narrow, the landscape is a very narrow geometry. It is only expanding along one direction, and only along the other direction it expands very slowly. And this will cause a lot of issues because of you cannot pick a large step size to implement the algorithm. If you take a large step size, very easily you will cross the line and jump to somewhere that has a higher objective function value. So this is the problem. And in fact, we have shown that the complexity for gradient descent is given by kappa times log 1 over epsilon. Okay. So it is already shown in this result. If you have a very big kappa, the complexity becomes very bad. This means that for this type of quadratic problems with a large condition number, gradient descent may not be a good method. So what could we do? One thing we can observe is that if we implement gradient descent, and this will be the gradient descent update rule. So in this update rule, the problem is caused by this Q. Every time you will multiply this difference vector by the matrix Q, but this Q matrix is very biased. So every time it will scale the vector in a very biased way towards a very biased direction. So a very simple solution is to get rid of this Q. So to do that, we can multiply an inverse in front of the gradient. Right? And this inverse, Q inverse, is to rescale the gradient. Right? Now think about that. With this Q inverse term, this will cancel with that Q in the gradient. So the update rule now simply becomes this one, right? And that Q disappears. And this iteration, this is a very simple iteration. In fact, if you choose eta t equals to 1, you will immediately get x star in one iteration. Right. If you set eta t equals to 1, these two cancels. Now xt plus 1 is x star. You will jump to the optimal solution in one iteration. Right. So this rescaling trick seems to be very effective for this problem. And we have a very nice interpretation of this trick. So this update rule, well, we call it rescaled. You can call it rescaled gradient descent because it's gradient descent with that Q inverse term. This update rule is equivalent to the following optimization problem. You can rewrite this update rule as a solution to the following optimization problem. Well, again, we have this linear term that we have seen before, but for the quadratic term, it's different. Here, we are no longer using that Euclidean distance. Right? Remember, if you go back to this slide, we are using a very simple Euclidean distance. But now, the distance we are using is a rescaled distance. Okay. Right. You can check this is a valid distance metric, but it is defined based on a positive definite matrix Q. And because Q is P positive definite, so this quadratic term is guaranteed to be non-negative unless x equals to xt. So it is a valid distance metric. But it is more, you can tell that this distance metric is more adapted to this problem, because the problem we are looking at is based on such quadratic function. It is related to Q, but now the distance metric we are using also depends on Q. So this will better fits the geometry of the underlying problem. So connecting these two, we can tell that sometimes if we choose the right distance metric, the resulting algorithm will be very efficient. Okay. We will, like in this problem, we will converge in one iteration. We will get rid of this large condition number issue. Because sometimes this condition number can be 10 to the power of 3 or even 4, depending on the problem. Okay. So this is one illustrative example. In fact, and this is, I think this is a visualization of this metric, of this algorithm. Basically, once we introduce this Q inverse, it feels like we are transforming the problem, transforming this ill conditioned problem, or with problem with a large condition number into a problem with a small condition number, where everything looks more regular than before. And this problem is much easier to solve. Another example is optimization over the probability simplex. In many cases, we want to look for a probability distribution. So we want to minimize fx. Well, x is a probability distribution. Precisely, x is what? Is a positive vector. All the entries are positive and they sum up to 1. It corresponds to a probability distribution. So we call this constraint the probability simplex. And of course, this is a constraint optimization problem. Of course, you can use projected gradient descent, right? You do a gradient descent followed by a projection onto the simplex. And there are some results to show how to do the projection on the simplex, but it is not that easy, because this is even in 3 dimension, you can tell. In 3 dimension, the simplex corresponds to this surface, this triangular surface. And projection onto the surface is highly non-trivial, because it depends on where the point is. If your point is here, then you are projecting onto this side, right? But if your point is here, you are projecting onto this side. And so the decision boundary is not very smooth. You have to do it very carefully. But this is only for 3 dimension. Once you go to, right, if the distribution is over hundreds of dimensions, it's even more complicated. You can do projected gradient descent, but it is not recommended, because usually we do not measure the distance between probability vectors using the Euclidean distance. Instead, in probability, we usually measure the distance through some divergence measures like KL divergence or total variation. So the central idea of mirror descent is basically instead of imposing the Euclidean geometry, we want to adjust the gradient updates to better fit the geometry of the underlying problem. And this can make a huge difference. Right. Now let's look at this mirror descent framework. The update rule is based on what we have shown before. It is a very straightforward generalization of the gradient descent. Now let's go back to this. This is the projected gradient descent update. Well, we have just shown that the projected gradient descent update is equivalent to the solution of this optimization problem. And now you look at this optimization problem, it's a quadratic one, basically a local Taylor expansion plus a Euclidean L2 distance. Okay. Now what we will do in mirror descent is simply change this distance to a general distance metric. Okay. And this is the mirror descent update. Right. You can see the only thing that changes is the last distance. Here we are no longer imposing the Euclidean distance. Instead, we impose a very general class of divergence metric. We call the Bregman divergence. This kind of you can sort of treat this divergence as a metric that measures the distance between x and xt, but in a different way, right? Very differently from the Euclidean distance. And this phi in the subscript is a function that we use to define this divergence term. And the definition is defined as follows. The Bregman divergence between x and z, 2 points, under a function phi is defined as follows. Phi x minus phi z minus this dot product term. Well, this phi function has to be a convex and differentiable function because it involves the gradient of phi. There's a lot of long history for this Bregman divergence, and we can see some examples to convince ourselves that this is a good way to generalize the distance. Okay. So maybe, yeah. This is nothing but just, yeah. So let's just look at this Bregman divergence. So this divergence is kind of similar to the square Euclidean distance. In fact, we will show that the square Euclidean distance is a special case that is included in this family. This can be sort of, this term can be sort of treated as this locally quadratic estimate based on the mean value theorem. So this is basically measuring the distance between x and z, but scaled by the Hessian matrix of this phi. Okay. And hopefully, if you pick the right phi function, that matrix will fit to the underlying geometry of your problem. But let's look at some concrete examples of Bragman divergence. Now, previously we have looked at this kind of distance, rescaled distance. This is a distance metric scaled by a matrix Q, where Q is positive definite. This distance can be generated by phi Bragman divergence with such a phi. We pick this phi, pick this quadratic phi, plug it into the Bragman divergence formula. You can show this is the proof. This is the Bragman divergence formula. Now you have this phi. Plug it in one by one. You can check. In the end, you get that distance. Okay. So if you choose this phi, you get this distance. In particular, if you set Q equals to identity matrix, right? Which means if you choose phi to be 1/2 x L2 norm to the power of 2, then the distance simply becomes the standard Euclidean distance. If you choose this phi, then we recover the standard Euclidean distance. Right. So this is a special case of this Bragman divergence family. And this is what we just shown. Basically, you can write. We just discussed about this scaled gradient descent, right? Now the idea is that we can rewrite this update rule into the following optimization problem. Okay. Now I will skip these steps, but they are basically introduced in different constant terms so that you can make it a complete spell. Now, in the end, what we have is what? This is a quadratic term. The last line is quadratic term. Inside this, okay. Inside this parenthesis, this is like a scaled gradient descent. Yeah, this is like a scaled gradient descent. And then we will, and then the entire quadratic term is basically projecting this point onto the set C, but following such a scale distance. Right here, we are looking at the scale distance based on Q. So this is projection of this point based on this weighted L2 distance, which is a scale distance by the matrix Q. And this is another example, KL divergence. X and Z, KL divergence between X and Z is defined as follows. Here we assume both X and Z are on the probability simplex, meaning that their entries are positive and they sum up to 1. And then we can measure the distance of two distributions using the KL divergence. Now, this KL divergence can be generated by Bragman distance using such a function. If you define phi x to be the negative entropy So entropy is the negative of this thing, right? So we call this negative entropy. If we choose such a phi, we can verify that it becomes KL divergence. And this is the proof. This is the definition of Brakman divergence. Now you plug in the definition of phi, do some calculations, you can verify that it is indeed the KL divergence between two probability vectors. Okay. And this one is highly, is highly non-Euclidean because we have log. It's no longer a Euclidean metric. And even more, this divergence is not symmetric. XZ is different from ZX. So this becomes totally different. Okay. And let's say if we look at an optimization problem, well, X is constrained to be within the probability simplex. What we can do is we can choose such a KL divergence and design the mirror descent algorithm. So the mirror descent will become what? Is simply, right, simply this right, we have this dot product term plus 1 over eta t. Now we choose this to be KL divergence. If we choose this, if we specify this Brakman divergence as the KL divergence for this problem, okay. If you are dealing with an optimization problem over the probability simplex, now we use the mirror descent update, but we specify the divergence, the distance metric, to be the KL divergence. Okay, so we use this KL divergence. And then you can check this this algorithm update, right? It is specified by an optimization problem. You can check this problem has a closed form solution given by this form. This is the ice coordinate of xt plus 1 that's given by this form. You can check that. You have to solve this problem by yourself. That is a linear term plus a KL divergence term. And they are separable. Linear term can be decomposable over the coordinates. KL divergence also decomposable over the coordinates. And you have this constraint. You can do whatever, you can use maybe some Lagrangian multiplier methods to get a closed form solution. But indeed, you have this. So this turns out to have a closed form solution. And it is very nice, very naturally fit into the problem geometry. Why? Because if you look at this expression, the right-hand side automatically has a normalization factor on the denominator. So no matter what you do, the xt plus 1 you get is always on the probability simplex. It's always, and it is always positive because of these exponentials. So it's always positive and they sum up to 1. The automatic is satisfied. So this is actually a very classic algorithm called the entropic descent or exponential gradient descent because of those exponentials. And the update rule is very simple. You just need to compute the gradient. And based on the gradient vector and the xt, you can do this update rule. You can do this update coordinate-wise, one by one, but you can do it in parallel. This is much easier than performing a projected gradient descent, because if you do projected gradient descent, projecting on this simplex is very complicated. But here, introducing the KL divergence automatically handles this constraint. And we have some other generalized KL divergence. I don't know the details. There are some other divergences based on matrices, based on eigenvalues of matrices. Again, I will not. I think these are used in quantum mechanisms. We're looking at the eigenvalues of matrices, but they are pretty similar. It's basically the KL divergence between the based on the eigenvalues. And there is a list. There is a table. The table could be bigger, but these are some of the popular ones. Well, for different phi x, these are different phi x. It can generate different types of divergence, Bregman divergence. Squared norm, right? We have Euclidean distance, first row. Entropy, we have KL divergence. And we have other entropy terms. Okay. So basically, even an optimization problem, you may want to choose a proper divergence term, so that the mirror descent algorithm fits into the underlying geometry of your problem. And in the next lecture, we will talk about the convergence properties of this mirror descent, and we will see that if you choose a proper divergence term, the complexity can be much lower compared to the gradient descent method. Okay, so please start working on homework 4, and I will see you on Thursday.